Welcome to this XA 2021 talk. In this talk, we're going to discuss how to measure the pros and cons of using software dependencies with a novel metric, technical leverage. It measures dependencies and yet talks about exposure, risks, and security. This research was partly funded by the Horizon 2020 Azure Moss project. Let's start discussing how software development changed. We are taught to see software as a large animal, controlled by its developers. After all, it's their own code. If a security vulnerability is found, they can go and fix it. But this is no longer true. Now developers use free open source software as building blocks. In this way, they can focus on their own added value functionality and rely on other people's code for everything else. Homegrown code may be only 5%, and dependency code is 4 times bigger than own code. Developers are not actually writing a big homegrown control animal. They're balancing on a pyramid of many shifting rabbits, software dependencies. Yet, code coming from dependencies is still code. It can have bugs and security vulnerabilities. You have to wait for a fix coming from upstream developers and must update to the new version, lock, stock, and barrel. Its new functionality, which you may not need, may introduce breaking changes. If there are serious vulnerabilities in the dependencies and you decided not to update it, you may end up in the evening news. We need to have an indicator to understand our exposure. And here we can learn something from finance. 30 years ago, in a landmark paper in the communication of the ACM, Eric Allman popularized the notion of technical debt, first introduced by Cunningham 30 years ago. Shipping first-time code is like going into debt. This is a very active research area, and everybody agrees that technical debt describes unfixed issues accruing in one's own code. But now, internal own code is 5%. What about the rest? How do we account for dependencies? Enter technical leverage. So, own code is the part you developed. Dependencies, both direct and transitive, are other people's code that you reuse, but they control. In finance, people borrow money to multiply the effect of their own assets. Leverage is the ratio between debt and equity. Other people's money versus your own money. Applied to software, technical leverage is the ratio between other people's code, software dependencies, and your own code. In finance, leverage multiplies income, but it multiplies losses as well. The same holds for software. Leverage allows developers to develop their project faster and focus only on the distinguished functionality. However, it increases the size of the uncontrolled software code used by the project. It increases the risk of having a security vulnerability. Do you remember Lehman Brothers? They leveraged 30 to 1. At some point, even 60 to 1. What about Software Brothers?
Let's see some real-world software projects. We selected the 200 most popular FOSS Java libraries used by a multinational software development company and its customers or internal production level software. This resulted in more than 8,000 distinct library versions, or GAVs in Maven terminology. For simplicity, we focus only on the leverage on direct dependencies. Every point in this scatter plot is a software library. On the x-axis, we have the library own size, the homegrown code of a library. On the y-axis, it's technical leverage. Both axes have logarithmic scale. Consider the Network Application Framework library io.netc It has more than 175,000 lines of own code. Another example, Java Spring Framework. This is a pretty big as well. around 500,000 lines of code in total. But what about its own code? 200,000, 100,000, 10,000, 1,000? In fact, around 1,000 lines of code. Wait, but how is it possible? The org Spring framework, Spring Aspects library, have a leverage of more than 400. Which means that for every line written by its developers, there are 400 lines written by somebody else. Ioneti all is smaller, but not that small. It has leverage of 7. We clearly see the relation between direct leverage and own code size. The bigger the library, the smaller the technical leverage. The median technical leverage reduces from 15 for libraries with small medium code base to 0.5 for libraries which have a big own code base. So, libraries with a small code base stands on a very large number of pygmies. They have a great leverage. Or in other words, they ship other people's code. Leverages multiply profits. So you ship a functionality for 1.5 million lines of code, but you only write 150,000 lines. This is a great business opportunity, isn't it? But do you remember Lehman Brothers? Here we have the vulnerabilities present in the library on the x-axis, and on the y-axis the distribution of the leverage of libraries having that number of vulnerabilities. A pattern is clear. As leverage increases, so does the number of vulnerabilities. There are some exceptions on the very right of the plot. Some libraries with a high number of vulnerabilities have a relatively small leverage. They have a high number of vulnerabilities just because they are big. If you have more than 100,000 of lines of code, a paltry leverage of 4 means shipping more than 500,000 lines of code. So, if you want to heavily leverage on others' code, you have to accept a high security risk. To recap, technical leverage is a simple yet effective metric to understand your exposure to dependencies in your software projects. For libraries in our sample with a small medium own code base, usage of dependencies pays off. Leverage and ship more than 4 times your own code. You'll need just 2 extra days for each release on average. But the same 4-fold increase in the total code size of a library means 60% increase of a chance to have a vulnerability in your library. Maybe in your code, maybe in somebody else's code. If you're interested in the idea of technical leverage, please visit the techleverage.eu website. The website allows you to check technical leverage for some Java libraries in the live demo section. Find related publications, empirical dependency studies, or introductory magazine papers, blog posts about software dependencies. Thank you for your attention.
Good evening, everybody. My name is Davide Fucci from Blekinge Institute of Technology in Sweden, and with me I have Ivan Pashenko and Fabio Masacci from University of Trento and Free University of Amsterdam. I would like to know if there's any questions from the audience. Let me check the chat. Okay, while maybe the crowd warms up a little bit, I'm going to start asking few questions I have, especially about this technical leverage that you kind of borrow from finance. I'm wondering when you define technical leverage as debt over what you own. What is this debt that you're really talking about? It's line of code, but in the financial metaphor, debt is always something that you pay back to someone. So how does that apply to your work or to the idea of technical leverage you propose?
Go ahead, Ivan.
Okay. Yeah, thanks, David, for this question. And this is so what we thought about this. So basically, when you import a software dependency, right? So in this dependency, at some point of time, there will be some bugs and maybe even vulnerabilities discovered at a later point of time. And these then these vulnerabilities will be fixed probably by developers of this library, right? And so when they fix, you're still using your previous version. And to update this code, you actually need to update the library itself. So you need to adopt the fixed version of the library. And this might require not just a simple change in the configuration file, but also might require some changes to do some maintains, to do some additional testing of your project. And this is exactly the thing that is basically we are like.
Okay, so basically the idea that I see. So when you import a library, you expect that you have to pay back some cost of fixing.
It's not necessarily debt. It's an opportunity as well. So that's why the financial metaphor is there, right? So
yeah.
In this notion of technical debt is always something you have to pay back. But here is also the idea of the financial metaphor is you use others people's code or other people's money, and this can be also an opportunity. It's actually an opportunity for most of the cases. And that's why it's not, there's always a negative connotation. And that's why also the title of the paper says opportunities and risk. It goes in both ways, right? The classical notion of technical debt is you have to pay back. But this also works in a positive sense. So you use other people's code, and therefore you can be faster in shipping because you don't have to develop the things yourself, and therefore you can make more money. Okay, but because it's other people's code, maybe they're not as good as you wish them to be. So it goes both ways, right?
And let me see, still no more questions. So maybe I can ask one more about the formula again. So I've seen that in the formula you include in the depth also the standard library of the language that you're using, but you assume it as a constant, I guess. So is it maybe in the light of this formula to prefer maybe languages that have a larger standard library? I'm thinking of, for example, languages like Golang or Erlang, which ship a lot of functionality out of the standard library, rather than languages which have a really minimal standard library, which therefore maybe necessitate to borrow more code from third-party libraries.
Okay, so if I may start, so basically we include this third term in the formula about the standard libraries because if we want to compare technical leverage between the ecosystems, for example, Java and Golang, right, then this will not be constant. But if we want to compare libraries within the ecosystem, then we can assume that the standard library is kind of constant, right? So that's the notion, yeah. And about the preference of the language, well, this really depends, let's say. Again, it depends on the opportunity and the risk that the language gives to you, right? So for example, if we are talking about C++, then C++ gives you a lot of opportunity to develop very fast software, but at the same time, it might be risky because it's very easy to introduce a vulnerability.
Okay, thank you.
So remember, it's important to remember that this is a two-edged sword, right? So it increases your exposure, right? So you use a lot of standard libraries, and therefore this is good because then you don't have to develop yourself. But at a certain time, the standard libraries are, some cases they may have vulnerabilities that you don't know, and then the same happens for Linux, right? You have sometimes there's a vulnerability in a standard library in Linux, and because it's so big, that may happen, right? It's always the trade-off. So you have less control, right? In a sense, that's the idea, right? The more the libraries are there, the more you have less control over it. Then, of course, you can trust the people that develop the standard libraries better than the people that develop these particular libraries. Indeed, that's what we said also in the paper. You should distinguish between in finance, they do distinguish between the type of money you have, right? You have stocks and obligations and other things, restricted bonds. And so also in this case, maybe you want to distinguish between different type of libraries that you borrow against your own code. This, of course, assuming that you have a better control of your own code, which is not necessarily true.
That's indeed true. And let me see. So maybe a minute. So maybe one more from my side. This is more general and speculative, really. I think that this idea of technical leverage can be from libraries to other systems that your system uses in order to function, and how this, for example, can impact, or what's the relationship with supply chain kind of attack. Imagine that you have a system that uses a system to offer, I don't know, some sort of functionality, and this in turns supply chain attacks, for example. Do you see that this technical leverage still applies to these cases, or can be expanded in the definition? Or
I think supply chain attacks are included into the definition because you leverage on something that is part of your software supply chain. So then it should be able to apply it in this definition. But when more details of the things, but for instance, one of the proposal from one of our colleague from industry was to just evaluate technical leverage, but not even looking at the source code, just look at the raw raw library, like binaries, and count the bytes in the binaries and see what happens if this still really works.
all right.
Yes, indeed. So basically, we'll need to find the right proxy for the value that we borrow and that we have. Yeah.
Okay.
Yeah, and so in the last minute, so if we still don't have questions, I would like to mention that we
feel free to mention.
Yeah, we also have a website that you can use and can play with. So I'll share the link to the chat maybe. And yeah, so if you're interested, here you can find some additional information about the metric itself, and you can have a live demo to calculate the technical average for different Java libraries. Find some additional papers, related publications about spread on metrics.